Begin.
Okay, well, Rob, thank you so much for organizing this, and thank you to everyone on the call for attending. I've been really excited to share what my team has learned over the past 6, 7 years developing custom equipment, benchtop automation, turnkey test fixtures, machine design. Um, I always tell my team that I think clarity is very, very important. So I want to share a little bit of clarity here. I would love to say that I'm here solely out of altruistic motivations, but that's not entirely true. My hope is that uh, someone here will now or in the future have a need to outsource the development of automated equipment or turnkey test fixtures, and will think of pipeline. And if that happens, then I will feel like this has been a wonderful success. So if your organization or organizations that you know of have need to develop custom equipment, please think of pipeline design and engineering. Now that that's out of the way, let's jump into the webinar, how to design test fixtures. Um, uh, we, like I mentioned, pipeline, we develop automated equipment, test fixtures, machine design. And I'd like to start with the definition of a test fixture, at least my definition, because it can mean a lot of different things to a lot of different people. A test fixture can refer to something very simple or very complex. So it really spans a wide range of different definitions. The way I like to define a test fixture is any tool, machine, or piece of equipment, typically within an R&D or manufacturing environment, that facilitates a measured operation in a highly accurate and repeatable manner. And these test fixtures are typically used in three areas of development: characterization, verification, or production of a device. As far as measured operation, let me speak to that just very briefly. What is a measured operation? That could be pushing a button. Maybe you have to cycle test a button 10,000 times to ensure that button is not going to fail. Well, the operation is pushing the button, and the measurement aspect of it is how much force is required. So that's an example of what I mean when I say a measured operation. What does a test fixture look like? Here are two examples, kind of bookending what I mentioned earlier, which is that there's a range of equipment or tools that can be considered test fixtures. The one on the left is fairly simple. There's a little rack and pinion mechanism going on there. That particular fixture was mounted to the base of an Instron, and the white plunger, where you can see here my mouse is hovering over it, that was attached to the load cell of an Instron test machine. And then a device was clamped inside this holder. And this little arm right here is attached to the pinion gear and would rotate back and forth as the Instron cross arm, the load cell, moved up and down. And all that did was rotate a lever on the device. So the only purpose for that particular fixture was to rotate a lever on a device and to measure the force required to do that rotation. So a fairly simple fixture. On the right side is an example of something much more complicated. Now, this particular standalone fixture did not rely on external measurement equipment like an Instron test stand or anything like that. It was all standalone, built into a single cart. And this accommodated 5 different devices within a device family, and measured RPM of a shaft. And these devices, there was a shaft that was spinning. So a shaft that was spinning very fast, it measured that RPM. It measured the straightness of the shaft. It measured the input torque of the shaft. It measured the pressure decay of the shaft, or of the device. This particular device pulled suction. So it did all these things, and it was automated with some LabVIEW software that we wrote. And so the technician just pushed a button and this battery of testing would occur. And I wanted to give these two examples to communicate the fact that a test fixture can be something fairly simple, like the one on the left, or something fairly complex, like the one on the right. Some people, when I say test fixture, they think of just a little jig maybe that's used to hold a device in place so you can drill a hole in a certain place. And that could be an example, but they're much more than that. We can get more sophisticated, more complicated, and more value overall in what we do. So what to know about test fixtures? There are three main things that I'd like to share today. These are the three most important things that I think we all need to know and understand about test fixtures. The first is that they're only useful to the extent that they can produce accurate and or repeatable data. And we'll get to that and or in a future slide. But for now, we'll just say that they're only useful to the extent that they can produce accurate and or repeatable data. The second thing is that people are the biggest source of inaccuracy and non-repeatability. So it's really important in our test fixture design that we minimize the interaction, minimize the human element, because people are always the biggest source of variability in test fixtures. And the third thing is the fixture itself must not alter the performance of the device being tested. So we'll go through all three of these in a little bit greater detail. There's a little bit of engineering humor for you, right? Why do you multiply by this crazy number? Well, otherwise the test fails. We've probably all experienced maybe some of that, or can relate anyway. If your test data isn't accurate, you almost might as well not do the test in the first place. The reason I mentioned and or in the previous slide was because there is an exception to that rule. Oftentimes, you're concerned with the actual values being produced by the device. How fast is that shaft spinning? How much force does it take to push this button? But sometimes the absolute value of the device's performance is not what's most critical to the test. What is most critical is the relative values. So you might be measuring the amount of force required to push a button, for example. And let's say that we know somehow it requires it requires half a pound to actuate this button, but our measurement reads 0.6 pounds. If we're in an event or a situation where the absolute value is really what's important, then we have a problem. But if we're in a situation where we don't care as much about the absolute value, what we really care about is relative values between all the devices, then even if our test measures 0.6 pounds and we know it's supposed to be 0.5 pounds, if all of the devices measure at 0.6 pounds, then we're probably okay, because what we care about are relative values. And this is important because sometimes measuring absolute performance values could require additional work in designing the fixture, perhaps a more expensive fixture, when if all you're looking to do is set a baseline and compare relative values, it might be less expensive and easier to design that test fixture. So that's why it's critical that your test fixture produce accurate and or repeatable data. And you as the engineer, it probably needs to come down to good engineering judgment as far as which one you need in your particular application. Let's talk about human interaction. How many of you can draw a straight line by hand? Now, I cannot. I took a drafting class in high school, and my friends always made fun of me because I could not draw a straight line to save my life. If I didn't have a straight edge with me, it just wasn't going to happen. In our experience, by far the biggest source of variability is the human operator. The more we can do to remove human interaction, the closer your fixture will come to being both accurate and repeatable. This isn't because technicians aren't careful or capable of following instructions. It's nothing like that. It's simply because our clumsy human paws lack the dexterity to produce high accuracy measurements, let alone to do so in a repeatable manner. and without that high level of accuracy and repeatability, engineering teams can't really be certain that their device is performing correctly. So is it the device that's giving us these measurements, or is it the way that the human operator interacted with the test equipment? So if there's a problem with pure accuracy or failed repeatability, oftentimes it's just due to human interaction. So it's a good practice to minimize human interaction as much as possible. And number three, a good fixture should simply be a conduit through which the device's actual performance flows and is measured unaltered in any way. An exception to this might be the situation we talked about earlier, where you're more concerned with relative data than absolute data, but outside of that situation, your fixture should never alter the device's performance.
We have a black screen here, Aaron.
Thank you. Yeah, thank you. I should have mentioned that. That's okay. I'm going to play a video here. It'll start in just a second. And this is an example of something we did where we needed to eliminate the effects of human interaction. So it should start playing. There we go.
I can see it. That's excellent.
Can you hear the audio?
No, not right now.
Okay, I might just have to speak through the audio myself. But for some reason, it's not. I wonder, is there a way that I can share audio as well? Share my computer audio?
I don't think so in this format.
Okay. Well, I'll just try and talk through this as it plays. So we had to, well, that's not going to work. The audio is playing for me and I can't really talk through it at the same time. I get kind of confused. Maybe we'll just skip this slide. All right, let's just go to the next one. So why does all this matter? Test fixtures are a human's way of, in data form, seeing how closely a device actually performs relative to its intended performance. And Mark Twain once said, "It ain't what you don't know that gets you into trouble. It's what you know for sure that just ain't so," which I think is a really relevant statement to testing and test fixture design. If we're getting data that we think is correct but is actually not, that's what's really going to hurt us. So it's really critical that we design test fixtures in a way that don't alter the performance of the device in any way. And good data, of course, leads to good decisions. Bad data leads to bad decisions. Some of you may have wondered in the past when you should start or when you should use test fixtures within the product development process. And there are three main areas where we have found test fixtures to be often employed and very useful. The first one is when you're characterizing a device, and this is typically performed during development. Then there's verification testing, which typically takes place either after development or after a development iteration, right? Oftentimes there are quite a few different iterations as you develop a device. So verification testing comes after development or after a development iteration. And then there's in production, of course. You know, you're through development, you're into manufacturing, and you need some kind of test fixture to facilitate assembly or do some kind of inline inspection. So those are the three areas where test fixtures are most commonly used: characterization, verification, and production. Here's an example of a test fixture for characterization. I'm going to provide examples of each of these three: characterization, verification, and production, just to make it really clear and help everyone understand what it is I'm referring to. So this particular device wasn't technically a medical device. It's a massage device. And you can see in that picture there how there are these two flexible spheres that sandwich a person's forearm. And as you move your forearm in and out through those balls, it imparts a compressive load onto the forearm, and it feels really nice. For any of you who have used a mouse a lot and have maybe the kind of that repetitive stress injury, that's what this device was designed for. So we needed to correlate what felt like the quote unquote right amount of compression with actual engineering numbers, so that we could use the design, so that we could ensure the design was robust enough to withstand those loads. And so we needed a fixture that would help us characterize that compressive load. So what we came up with was relatively simple. There was this aluminum frame that kind of mimicked the shape of the device, and then we put the actual roller balls inside this fixture, and we allowed one of those roller balls to slide freely back and forth, and then put a force gauge on that sliding ball unit, so that when you put your forearm in there, it forces the two balls apart just like it does in the regular device, and you can read force data. And that's how we were able to characterize the amount of force being realized in that device. And then we used that force data to ensure the actual product was designed in such a way that it would never fail when those loads were realized during practice. So that's characterization. Verification, this is a picture we saw earlier. It's this cart, and this was used once the device was already developed and the customer needed a way to measure the RPM and that input torque, the pressure response, shaft straightness. There were a few other things. So again, the device had been designed and they just needed to verify that the performance of the device was as intended during the design. And then here's one for production where the device had already gone through verification and it was into production now, and the customer needed a way to, during production, do some inspection, some inline inspection, and make sure that some of the optics in this particular device, it was a bronchoscope, were working as intended. And so that's an example of a production test fixture. How about planning? When should we start thinking about test fixtures? You're going to want to start this relatively early in the process, and I can get a little bit more specific about that. Typically, when you start thinking about design inputs, that's when you want to start thinking about your test fixtures as well. So you've already got your user needs, and now you're into design inputs. You're trying to define those engineering requirements that need to be met in the device. And if you run into a case where you have a design input and you're starting to think about test fixtures, okay, what kind of test could we run to verify that design input? If you can't come up with a test or a test fixture that you think would adequately verify that particular design input, then it might be an indication that it's not a great design input. So this is also a check for your design inputs. We typically, for a simple test fixture, you probably want to allocate anywhere from 2 to 4 weeks to develop and manufacture it, depending on how you're making it. But for even a simple test fixture, you probably want to allocate 2 to 4 weeks in your schedule. Of course, the more complex the fixture becomes, the more time you should allocate. For what we've seen, it's very rare that a test fixture requires more than 6 months, and that's for something very complex like that cart that we looked at earlier. But much more common, especially when we're designing, 3, 4, 5 different test fixtures that are all being used on the same device. So you have this family of fixtures to verify the performance of a device. You usually want to put 2 to 3 months into your schedule for just the test fixture development. Make sure you plan it into your schedule. Don't make it an afterthought, and think about assembly as well, especially for some of these more complicated test fixtures. We have run into that in the past where we have everything designed and fabricated, and now it's time to assemble it, and it takes longer than you expect to do the assembly of the test fixture. All right, so we have kind of a system that we use. Call it the pipeline wave system. Short tangent here. I grew up in Hawaii surfing, and Pipeline is the name of a very famous surfing beach on the north shore of Oahu. So the name Pipeline is just a throwback to my days surfing in Hawaii, and it has nothing to do with oil or refineries or anything like that. So the pipeline wave system seemed like a good, it's an acronym, but it seemed like a good marketing title to use. We see waves in engineering as well. Workflow accelerations and validations for engineering. Ask me how long it took to come up with that acronym. But the pipeline wave system is a 5-step process that we use internally, and I recommend to other teams when they're designing test fixtures. Starts with having a really solid understanding of what that problem is. All too often we jump into a design without fully understanding what the problem is. So define the problem and define the functional requirements of your test fixture. Second one, and we'll get into a little bit more detail on each of these. I'm just going to go through them fairly quickly right now. The second one is to ensure that the device is fully constrained and unambiguously positioned. And then we want to, of course, minimize reliance on human interaction. We've talked about that already. Ensure the fixture will not alter device performance. We've also talked about that. And select appropriate materials. So let's jump into this first one, understand the problem and define the requirements. If we don't know the rules of the game, then how can we know whether we've won, right? We need to understand what defines success for our test fixture. So here is just a really basic example of what a fixture requirement might look like. We start with the user need, right? Must be able to pass shaft of a laparoscopic device through a trocar cannula. All right, so how do we take that user need and translate it into a fixture requirement? We could say that it has to work with customers' existing Instron test stand, accommodate misaligned shafts up to 5 degrees, measure only axial insertion force, no erroneous side loading, and allow the technician to swap devices in and out of your fixture without using tools. That is an example of what you might come up with for the requirements of your test fixture. Okay, the next one is constraints. Partially constrained devices are a problem that we have seen that leads to poor, inaccurate, or not repeatable data. So you can see in this picture that we've got a device. Doesn't really matter what the device is. It's some generic surgical device that has been clamped down onto the top of 80/20, and it might stay in place during the test. But what happens once you take that device out and put another one in? Chances are the second device is not going to go into the same exact place because the constraints are not well defined here. It might slide a little bit to the forward, it might rotate a little bit. And so this is an example of a poorly constrained fixture. The second part of this number 2 step was unambiguous. We want it to be fully constrained and unambiguous. So the technician running the test needs to understand exactly how does the device fit inside the fixture. And I've highlighted in green the surfaces on this particular device holder that are a cradle for the holder. So these surfaces are based on the profile, the contour of the device itself, which makes it really easy for anyone to know exactly how the device fits in the holder. There's no way it's going to be placed in backwards or upside down or shifted to the right or to the left or up or down. There's only one position that device can fit into the holder. Poka-yoke, I guess, would be another way to say that. Well, I've got another video here, so I'm gonna skip that one because actually this one doesn't have any volume, so I can play this one. Let's before I press play, let's say that you need to move a device in a very specific trajectory in order to perform a certain test. Now, there are a few ways that you could do this. You could fully automate it, or you could just use the technician's hand, or there is a nice balance that we like to call hand automation. So I'll play this video. So that's what the fully automated approach looks like, where you've got a motor and a linear actuator, and your device is moving along a defined trajectory, and it never changes. Here's what fully manual might look like. I'm just kind of using my mouse as a surrogate for a technician's hand, moving it back and forth. You can see that it's not moving in a very straight line. And then here's what we refer to as hand automation, where you get 80% of the value for, in this case, a lot less than 20% of the cost. And that's a very economic route to pursue. So when you're considering how to minimize reliance on human interaction, if it's warranted and there's a budget for it, fully automated is great. If you need, if you don't need it to be fully automated, but you still want to get most of the advantages of automation, then consider a hand automated approach where maybe you're using some rails to guide it and a carriage to guide the device's motion on that rail, and then a technician's hand can just be what moves it back and forth, and that'll get you a lot of the value from the fully automated approach with a lot less cost. Okay, we need to ensure that the device does not affect performance, and there are a lot of this comes down to good engineering judgment and experience, right? Understanding the mechanics of your test fixture and how it may or may not affect device performance. But there are a few areas where this is your low-hanging fruit, so to speak. So you want to minimize friction whenever possible. Maybe your device, your test fixture has some motion incorporated into it, which is very common for test fixtures. Using open bearings where possible is a good way to minimize that friction. A pro tip, if you're using linear ball bearings, they always come with seals, but you can actually get a little X-Acto knife and cut those seals out, and that will greatly reduce the friction in your linear ball bearings. It's kind of a cowboy hack, so to speak, but it works really well. We've done that on more than one occasion, and it's worked out really well. You want to make sure that your device shape is kept within normal operating parameters. An example of that might be a catheter shaft. Maybe you're doing a torqueability test on a catheter shaft. You want to make sure that that catheter shaft is straight, not coiled in some tight radius, because that will or likely will affect your test results. Ensure that your device is always held in the same position, and this goes back to fully constrained and unambiguous positioning. Contoured device holders are a great way to do that, and make sure that the motion of the device is never over constrained by the fixture. And last one is material selection. Aluminum, stainless steel, and Delrin are kind of the go-to materials that many people use for test fixtures. We've also found them to be excellent candidates for test fixtures. Aluminum 6061 T6 is our go-to. We will usually hard black anodize that as well. Stainless steel 303, 304. If you're working in a wet environment, then 316 is a great option because it's very non-corrosive. And then Delrin is a great engineering plastic to use, very robust, pretty low friction characteristics if that is important for your particular application. UHMW is another one that we use sometimes when we need really, really low friction characteristics. In R&D environments, oftentimes the actual material doesn't matter as much. In production environments, typically you have to deal with RoHS and REACH considerations. So you have to make sure that your materials are RoHS and REACH compliant. But in R&D situations, that's typically not the case, and you might be able to get away with 3D printing some of your fixture parts. And we've actually had great success doing that. It's something I recommend to engineering teams as well, as long as you use the right kind of 3D printing material. And I will get into that as well in a later slide. Okay, this was just a funny video that I was going to play, but we can't. The audio is not coming through, so I'm gonna skip that one. All right, a few pro tips here. 3D print the holder. So we talked about that just a few seconds ago. Use helicoils and heat set inserts. Leverage off-the-shelf base plates and try to make it modular as much as possible. So let's go through those one by one. So here we have a 3D printed holder. Many years ago, any engineering team that's designing a test fixture is going to have to design a device holder for that test fixture. You always need some way to hold the device in your fixture. And the most effective way we've found to do this is by a contoured device holder, similar to what you see here. It's a contoured cutout that matches exactly the shape of the device, and then some toggle clamps that kind of clamp it in place there. What we used to do was to have that whole thing machined out of aluminum, which gets expensive and takes a while. You know, we probably would pay $2,500 or so, and it would take 3 weeks to get the part back from a machine shop. What we do now is we 3D print these holders, and there is a specific 3D printing material that I'll share later that we like to use. But 3D printing them, now we're getting these for, you know, $500 in 2 days. We 3D print them internally, but the customer is paying thousands of dollars less, and we're getting usable parts much sooner. I'm sure everyone here understands the benefits of 3D printing, so I don't need to extol its virtues too far, but some of you may not have realized that there are some 3D printing materials that are very appropriate for use in test fixtures and can save you and your teams a lot of money. Especially when using 3D printed materials for any areas in which fasteners are needed. It's a great idea to put helicoils or heat set inserts, threaded inserts in there. This part just shows how that was done. This was a 3D printed part that we made, and we used a combination in this one of heat set inserts that you just use a little solder iron to install, as well as these press-in inserts. And it's still a good idea to use threaded inserts, even if you're not using plastic parts. For example, if you have an aluminum part that you need some threaded holes in, we have had problems in the past where maybe there's a screw that needs to be installed and removed several times for whatever reason for that particular test. And what we have done is, or the problem that we have seen in the past is sometimes you'll get some galling. You know, you have a stainless steel screw that gets installed into aluminum threads, and the parts just seize and lock up, and it's really difficult to get the screw back out. So using some stainless steel helicoils, threaded inserts, resolves that problem. There are also, if you look on McMaster, there are some versions of helicoils that are locking as well, and that prevents screws from backing out on accident. So that's a great pro tip as well, to consider using locking helicoils. All right, pro tip number 3 is use off-the-shelf base plates. We have we've made extensive use of these off-the-shelf base plates. Again, it's a great way for your team to save time and money. You might spend $500 or something having a machine shop make a custom base plate, and that's not even taking into consideration the amount of time that your engineer needed to design that base plate. Or the alternative is there are companies out there that make these off-the-shelf base plates. They come in a lot of different sizes, and they all have pre-threaded holes in them, a pretty large matrix of holes, as you can see in this image here. That blue part is the base plate, and it makes it really easy to mount your device or your fixture components down in kind of anywhere you need to, having this matrix of pre-tapped holes all ready to go. And it's a lot cheaper. It's off the shelf, so you get it in a few days as opposed to a few weeks from a machine shop. Make it modular. Let's see. This one also has no sound, luckily, so we can play this without a problem. Here's one of our device holders, and it's in a cycle test machine. And it was designed in such a way that we can very easily take the device holder out of machine A, we'll call it, and put it into machine B. This is a completely different test machine, but it accepts the same device holder, and it's a tool-less operation. So any time that your team can design the test fixtures to be modular, that's gonna be a big benefit to you and the team. All right, we're coming to the end here, towards the end. Wanted to share this slide of resources. Mark Forged is a manufacturer of 3D printing machines. I think they advertise themselves as 3D printers for your factory floor. So they print parts that are really strong and chunky and perfect for test fixtures. That's what we have used for years and have had great success. Our customers love them. Again, they're perfect for the R&D environment where you're doing either characterization or verification. They might not be the right solution for production because there might be more stringent material requirements, but for R&D stage, they're wonderful machines. We're not affiliated with them in any formal way, so I'm not getting paid to say that. They're just great machines. McMaster, of course, everyone knows McMaster. All kinds of hardware and off-the-shelf components that might be useful for your fixtures. We have sent a lot of money to McMaster over the years. Fixture Works is a really cool company that has all these small odds and ends for fixtures. You may have seen those little quarter turn tool-less fasteners that in the video were turned 90 degrees in order to remove the device holder from the test fixture. And it's this company Fixture Works that sells those. The off-the-shelf base plates, that's from a company called Thor Labs. Highly recommend you check them out as well. They have tons of really neat engineering fixture related stuff. I think the company was started to support optical engineering, optics testing, but they're very useful for mechanical test fixtures as well. They've beyond base plates, they've got all kinds of other neat things like little XY stages and things like that. Futech is a great place to go for sensors, whether it's like a rotary torque sensor or some little load button. Futech has a lot of options there. I recommend you check them out. LabVIEW is a great tool for motion control. Some people don't realize that LabVIEW can be used for motion control and automation. They think it's just for data acquisition, and that's not the case. There are it provides some very powerful motion control and automation tools. The Mark 10 is it's a force gauge manufacturer, and their force gauges are a little bit different than the ones from Futech. Futech, you'll typically need a separate meter in order to read the response of the load cells, whereas Mark 10, their force gauges are all in one, so they have a readout screen built into the force gauge itself. Very convenient force gauges to use. They have, I think, torque gauges as well. For motors, Lexium M-Drive motors, we really like. They're integrated smart motors, so they have the controller and the drive all integrated. They're not separate boards outside of the motor. So they're made by Schneider Electric, Lexium M-Drive motors. And then for linear actuators, there's a company called PBC Linear that we've really enjoyed working with. For whatever reason, their linear actuators seem to be a little bit less expensive than some of the other folks out there like Parker. And they've worked really well. We've used them for many years, and that's a great source for bearing technology, especially linear actuators and things like that. So to review here, test fixtures must, right? These are the three most important things to know about test fixtures. Must produce accurate and repeatable data. They must minimize human interaction, and they must not alter device performance. And a quick checklist that all of you can take back to your teams and start using right away for developing test fixtures is make sure your requirements are very, very clear. Understand what the rules of the game are. How are you going to measure success for your test fixture? That's by defining requirements. Make sure that the test fixture or the device is held within the test fixture, fully constrained and unambiguously positioned. Minimize human interaction wherever possible, whether that's full automation or hand automation. Make sure your test fixture is not going to alter your device performance at all, and select appropriate materials, some of which are 61 T6 aluminum, 300 series stainless steel, and Delrin. Those are three of the heavy hitters. And that's it. Here's some contact information for you. There's my email address down at the bottom, and our website is teampipeline.us. We also produce a podcast called Being an Engineer. You can find that on Apple and Spotify and all of the major podcast platforms out there. So please check it out, Being an Engineer. And that's it. That's the presentation. So let's open it up for any questions that some of you might have.
Thank you, Aaron. One of the interesting points I thought you made along the way was if you're having trouble putting it in measurable terms, maybe you don't have your design input far enough along yet. I don't think I worded it quite as well as you did. Could you comment on that a little bit more? Give us maybe an example.
Absolutely. Let's see. I'm trying to think of an example off the top of my head. Okay, so let's say that you have a design input that says device must be easy to hold. And then you start thinking about, okay, how am I going to test that? How am I going to verify device must be easy to hold, right? There's not really like a metric that you can look at and say, yep, all right, it's easy to hold. There's nothing you can measure there. But if instead your design input was must use an elastomeric grip surface between 55 and 60 short A that has a matrix of protrusions that are equally spaced 1/2 inch and are 1/8 of an inch tall. You know, you can probably imagine kind of a bumpy grip, right? A soft bumpy grip, and that would be easy to hold. So that's maybe an example of how to define your user needs in a way that can actually be measured.
That helps out quite a bit. Do we have any questions from the audience? We had 7 other people logged in, and if you want to ask a question, just unmute your mic, or you can chat in the chat box, and I will read the question for you. One of the things that Aaron was asking me about before we even started here was when these machines are built, you have to validate these machines for production if you're going to be using them for production. And that involves validation of the equipment. It also involves some software validation if they're automated. So that's something to keep in mind when you're designing these machines. There's a process validation that most people are aware of, but there's that process. The basic concepts of process validation can be also applied to individual testing equipment. And the industry that I was working in before the medical device industry was automotive, and I worked there for about 1.5 years, and all the equipment that we had was automated equipment for testing as well as manufacture, and we had to validate all the equipment. So that was we had to have a positive test and a negative test for every single test that we did, or test article. And that was a lot of training to master, but it really served me well as I got into the medical device industry.
Hi, this is Marie.
Hi, Marie.
Hey, nice talk, Aaron.
Thank you so much.
This is maybe a silly question, but is there any kind of a clearinghouse for some of these machines, maybe that only get used during design input, but not so much during V&V, so that they're kind of only used once or used gently or something that, people can swap around and find?
Oh, that's an interesting question. I don't know of such a clearinghouse. Um, One of the issues we've run into is, or really our customers have run into, is that these test fixtures are typically so specific to a given application that it's hard to make something that's really truly a general use test fixture that can be shared with, other, companies. For example, if there was a company that just rented these out, or something like that.
Yeah, I know you had talked about some of them are modular, so pieces of them might be. And then, if something is sort of pushing a button all the time or turning a lever, that's silly, but maybe an opportunity for a business.
Absolutely. And one of the things that we are actively thinking about at Pipeline is how we could develop some sort of test fixture kit. So engineering teams had like a set of Legos that could really easily be put together, including some motion control and some simple automation. But I'm glad to hear you say that. It validates my thought that there maybe is a need out there for such a kit.
There's definitely in the companies where I've seen you build multiple generations of a product, and you have generation one, generation two, generation three. I've seen companies reuse those that test equipment, and they'll pull off uh, parts of the equipment that is product specific, but they'll still reuse a lot of the actuators, motors, and load cells. So there's definitely an opportunity to reuse the components of the equipment, but um, I don't think anybody has really looked at it from the standpoint of you're you're leasing or renting the hardware, and then give it back to the owner that will use it for the next customer. Um,
Interesting business model, though. It's an
yeah, it
interesting
definitely
idea.
is. The I think there's not a lot of opening for it to be used in when it's manufacturing, because you're going to use it for the life of the manufacturing process. But for verification equipment, I think it makes a lot of sense. Um, you had talked about using it at the beginning of the process. So you had three different times. One's for verification, one's for manufacturing, but the third one was more for characterization. Would that include characterization of like raw materials? If you had if you had a surgical mask, and everybody's building surgical mask machines now, but there's a lot of variability in the raw materials. So is there an opportunity there to use those types of equipment for uh, pre-qualifying or inline inspection of the raw materials?
Absolutely, yeah. Something we're working on is similar to that. With I can't really share too many details, but there is a material that we are having to characterize in order to develop a machine to handle this particular material. So yeah, there are absolutely opportunities for test fixtures to characterize materials during R&D phases of projects.
I really appreciate the time you spent with us today, and I'm sure that a few people will want to grab onto that list of contacts um, that you provided, as well as I wouldn't be surprised if you get a few calls. I'm going to be um, taking this recording, and I'm going to be uploading it to our YouTube channel. So for those of you that want to watch it again, it'll be on our YouTube channel. So if you subscribe there, then you'll get automatic updates to that. But I'll also send out a link to everybody that registered. So if you didn't register, check out the YouTube channel. If you did register, you'll get a link. Thank you very much, Sharon. And um, is the email there amoncour at teampipeline.us? That's the best email to reach you at?
That is, yeah.
Okay.
Teampipeline.com was $2 million, so we saved some money and went with the US version.
Got it. Oh, we get a couple of comments down below in the chat. So thank you very much. We really appreciate it.
All right, thank you.
Okay. Have a nice day, everybody, and thank you very much for participating.
Thank you. Thanks, Aaron.
Thank you, everyone. Thanks for joining.
Bye
Thank
bye.
you. Bye-bye.